All right, welcome everybody. This is session 2010, Severe and Extreme Storms, Detection, Prediction, Climatology, and the Future, Part 1. And Part 2 follows this afternoon. All right, welcome everybody. This is session 2010, Severe and Extreme Storms, Detection, Prediction, Climatology, and the Future, Part 1. And Part 2 follows this afternoon. Great. Welcome, everybody. This is session 110. Severe storms, detection, prediction, climatology, and the future, Part 1. And Part 2 follows this afternoon. Great. Welcome, everybody.
Hey Dave, I think if somebody has Event Moby running in the background, there's a
I'm trying to see if it's me.
Yeah, if somebody's not if people aren't speaking, they should mute their system. Okay. And those who are speaking, just make sure you don't have Event Moby running in the background because there's a delay.
Yeah, I think that was me. Sorry, folks. Okay, so right now I don't have the. Jeez. Now I'm looking, since I had to close the Event Moby, now I don't have the slides here. Hang on one second. Oh, there it is. Okay. As I said, session 2010, and the chairs for this session are myself and Professor John Hanesiak. We're going to have speakers that include John and Scott Kehler, Milena Alpizar, and Melissa Cholette, but we're going to begin with an invited presentation on Hodographs and Skew-Ts of hail-producing storms by Cameron Nixon. And his presentation is up, so Cameron, if you can take it away, that'd be great.
Awesome. Thank you all so much for having me on. It really means a lot, and I'm really stoked about this work. This is really what I did during my PhD in Central Michigan University. I worked with Dr. John Allen. He was my advisor, and I worked very closely with all the other people you see on this list and more by now. This is kind of this ongoing effort to better understand what parameters we need to be using to kind of at least have a shot at predicting hail out in the wild. So at least in the US, hail deals $10 billion in damage each year here. And then we have this saying, right, that we're in it for the protection of life and property. And although hail doesn't really kill as many people as tornadoes do, it's extremely hazardous to whatever you have in your yard, solar panels, cars, everything, roofing, etc. And so we know that these billion-dollar events are on the rise, both due to kind of the expanding bullseye effect as our cities get larger, and also perhaps with climate change. So the issue here is that we think that we know how to predict big hail. And we've kind of become kind of complacent and satisfied with this workflow that we've had for decades now. And we're starting to see that there's a lot of contrary, a lot of conflictions in what we're actually using and the physics behind hail growth. So maybe you've grown accustomed to predicting large hail with really big CAPE, right? Maybe that's really important. Maybe steep lapse rates are important for big hail, or really low freezing levels, or some kind of environment that supports a discrete supercell with, some nice looking Hodographs like this one. But the reality of this is that this right here is a state record hail sounding. What do we got here? We have a mediocre amount of CAPE, 2,500, 2,600, kind of moist adiabatic lapse rates all the way up. It's kind of that skinny CAPE. Hodograph, really nothing that, strikes me as particularly interesting about this sounding versus anything else. Kind of a moderate amount of SRH, mostly straight Hodograph, little veer back. So this is reality that we're dealing with these soundings that aren't necessarily crazy or insane or like three explanation points. Like we're dealing with kind of normal looking soundings. And so we want to go into, how does hail grow physically? A lot of people have a good conceptual model of tornadogenesis and how that might happen, and then how the environment might relate to that. But our understanding and our application of hail formation is usually a lot weaker. And so we'll discuss what's actually in a hail environment, what are some new parameters that we could be looking at, and then we'll go into some case studies. So on the fundamental level, how do we get large hail? Well, typically we want more hydrometeors or more hail embryos, more mass that could go into hail production. So this might require us having a broader updraft, right? The larger our storm and the more precipitation within that storm, the more of that mass could go into making really big hailstones. And then likewise, right, maybe our second dimension here, we talked about updraft width, now updraft depth. I mean, we've noticed, especially in the US, that hail size and the occurrence of really big hail is strongly related in time to overshooting tops, and then the overshooting top height of our supercell here. And however, most fundamentally, hail needs to spend time within this temperature region called the hail growth zone, somewhere between about -10 and -30 degrees Celsius. If you've ever dealt with the dendritic growth zone, this is kind of similar. This is the region that we've found to be most conducive for hail growth, and I'll just call that the HGZ throughout the rest of this presentation. But one of the biggest misconceptions about hail growth in the HGZ is that we need a really strong updraft to support these stones. This is kind of a controversial thing, but it kind of goes both ways. We know physically that larger hail needs a stronger updraft to hold it aloft. So if we have, a DVD-sized hailstone, we're gonna need a really strong updraft to hold it. However, our little bitty hail embryos, when they're first born within the storm, these don't need a really strong updraft. And in fact, if we have a really strong updraft, that can shoot these embryos straight up through that hail growth zone and not afford them any time to grow. We're really looking for kind of a longer residence time within this temperature region here to grow. So a lot of our hailstorms and in modeling, Matt Cumgen et al. Have been finding that generally weaker updrafts below that hill growth zone can better favor these longer lived trajectories within this hail growth zone. We don't want to start out with 30 meter per second updrafts here through that hill growth zone. We want to start off really slowly because our momentum within that hill growth zone then will be a lot slower. So then we can kind of tweak a bunch of things that might affect the residence time of hail within our storm. And these are things that especially Matt Cumgen has been looking at. Generally, this residence time is lengthened by having a lower freezing level, right? So if we have a really high freezing level and these are hail trajectories, they don't spend hardly any time in freezing temperature. Whereas if you have a much lower freezing level, of course, that stone will spend a lot more time above that freezing level. And so this is one of the reasons why hail is so popular in more mountainous or higher elevation regions, because generally you're bumping up your cloud base to just under your freezing level. And so in the high plains of the U.S. Or near the Rockies, you generally have a much lower freezing level as compared to storms out east. And so this is a really cool plot here of just the return intervals of really large hail here across the U.S. By Allen et al. And not only do you see that high plains and high elevation signal out west, but you also see it out east. A lot of our hail tends to follow the Appalachian mountain range here. You'll also see similar things like this in Europe with the Alps. So there's kind of this sneaky secondary hotspot of where hail is. But we could do a bunch of other things. Residence time can also be lengthened by having just a deeper and a broader updraft, right? Because the bigger proportions-wise our storm is, the longer that stone has to spend within that updraft. So generally larger and taller storms. But this residence time can actually be shortened by excessive vertical momentum here. Let's say you have a really intense updraft here. Again, these are the scenarios that can eject these hailstones out of that hill growth zone before they have time to grow. And likewise, if you have too intense of a mesocyclone, especially kind of a tornadic, a compact, low-level mesocyclone, these are actually not great for hail production. And so this has actually been found by the IBHS hail study here in the US, has found repeatedly that as supercells go tornadic, hail production can, slow or even cease completely. So it's this really cool kind of yin-yang start-stop relationship sometimes between hail and tornado production. And then this residence time can also be shortened by momentum in the horizontal. So if we have excessive storm relative wind here, this can also blow these hail embryos out of their favorable region within the updraft before they have any time to grow. So this is really abstract, so I'll show you how this works in data. So traditionally, most folks use some kind of CAPE, especially within the hill growth zone, to predict hail, maybe lapse rates, freezing level, bulk shear. And this is no surprise. As you look at the environments of hailstones here in the mean sense, you can see the size increasing here up to greater than 4 inches. As we look at these environments in the mean sense, you can see that all of these parameters become more favorable, except maybe for freezing level. You see the hodograph lengthen, you see more CAPE, you see your lapse rates steepen. So it's no surprise that we've been kind of using this to predict hail for the past few decades. But we also want to talk about these new concepts that are more directly related to kind of the physics governing the momentum of these hailstones within the storm and within the hill growth zone. Things like buoyancy, especially below that hill growth zone, which is really where the accelerations within the hill growth zone matter. Updraft width, updraft depth, right? The proportionality problem, and then our storm relative widths. So we've been finding that where the buoyancy is distributed within this column here really matters. And CAPE above this hail growth zone, especially kind of above the -10C point, this is one of the better discriminators of hail versus non-hail or SIG hail environment. So generally having more CAPE within this zone above that hill growth zone is usually a good thing. However, there's been some really mixed reviews on CAPE below the hill growth zone. And so we'll talk about why this might not be as good as CAPE above that. And so generally when we look at large quantities of data, we have these kind of stereotypical hail soundings. And this is kind of one of the most common here in the US. Usually features lots of SIN here and a relatively low freezing. So generally we have your LFC right up against your freezing level. You have a really shallow layer of buoyancy, but beneath that hill growth zone. And so we've seen this, maybe we just have a low freezing level to begin with. So again, our buoyancy beneath that freezing level is rather weak. Maybe we have something like this where we're in a high elevation scenario where our freezing levels are naturally lower. Maybe we have something like this where we have a really high LCL, which also forces a high LFC relative to your freezing level. Or even something like this. Maybe we have an elevated storm scenario where our LFC is way high and again, really up close to your freezing level. So in all these cases, you can see as we scroll back and forth, the buoyancy below that freezing level is relatively weak. And so this is kind of what we've been finding, and that a sounding like this might be a little bit less conducive to hail because we have all sorts of buoyancy beneath that freezing. So, and we'll touch on that later. But again, we've also found that wider updrafts can produce larger hail. This is largely a function of having more tighter meteors within your storm that could potentially go toward hail production, and also just having a much larger storm, and which can lengthen the residence time of hailstones within that storm. So how do we predict updraft width? Well, a significant part of this is the storm relative inflow, as was found by Peters et al. And generally stronger storm relative inflow, especially in this case, right? We have from 0 to 1 kilometers, we draw our inflow vector from our storm motion to the low levels of our hodograph. We get a vector that's about 30 to 40 knots long. So really strong storm relative inflow through a pretty deep layer. And so this stronger inflow can induce wider updrafts. And so generally when we have bigger hodographs, we can expect bigger storms that can potentially produce large. But the kind of X factor within this all is cell mergers, because regardless of our hodograph shape, more cell mergers and more updraft mass can still contribute to a much larger storm. So in this case, we had actually relatively small hodographs. This was out in western Kansas, late May 2016. And we had a bunch of storms come together, and then immediately they produced a large tornado and quite large hail. And so we've seen this time and again, that these mergers can briefly trigger a greater hail threat while their updrafts are merging. And then so on the other hand of the spectrum, right, we have depth, not width, but our depth. And we know that deeper updrafts can also produce larger hail. And we've seen this through overshooting top heights. So how deep can an updraft get? Most folks tend to use the equilibrium level. This is the region where we finally run out of Cape here and our parcel intersects the temperature profile. The issue with equilibrium level, though, is that we still have vertical motion past this level. This is just the end of our accelerations. Our updraft can sail past this level up here. I don't know if you could see this. I have this pesky little bar up here. But this is the most unstable parcel level. This is the level at which we finally deplete our cape, and we basically have an equal amount of convective inhibition up here as we do cape down here. So the level with which the updraft can finally attain after it runs out of vertical motion. So this is a really important distinction, because we actually found this to be quite an important predictor of hail size to talk about. And we know fundamentally that deeper updrafts can reach deeper above that hill growth zone. So I kind of colored this parcel path blue here to help you, see how much of our updraft here is within a favorable region for hail growth. Whereas if we have a really shallow updraft like this one, perhaps we really don't utilize all this cape here because of our small photographs. This is that E-cape concept. But let's say this is our parcel path and we, barely have a kilometer or two of depth into the hail growth zone. We can't get hail with this kind of sounding. We're largely warm rain processes do not have enough frozen hail embryos to give us much of a hail threat. However, let's say we took the same 9-kilometer deep storm and then we put it on top of a mountain where we have a much lower freezing level and much higher elevation. And now, we could still support hail with that 9-kilometer deep storm because most of our parcel path is above the hill growth zone. So to show this kind of graphically, this is going to be really confusing, but let's just focus on these two little areas that we've circled. And so let's say we have significant severe hail producing storms that are only 10 kilometers tall. Well, we're going to need a much lower freezing level, right? We're dealing with freezing levels that are sub 2,000 meters here with our really shallow storms. But to get the same size hail, let's say you have a 16-kilometer deep storm, your freezing levels just don't need to be as low. We're dealing with 4,000, 4,500 meter storms. So if we're dealing with shallower convection, that convection has to extend sufficiently deep within that freezing level to produce hail. And then I hope that's kind of a self-evident statement, but this is definitely what's falling out of the data. But most interestingly then, if we look at this kind of cutoff here in this graph, again, we're comparing the maximum parcel level here, which is above the EL, to our potential, the maximum hail size down here. We actually see a fairly one-to-one relationship here, basically telling us that as storms get deeper and deeper, as they get higher and higher maximum parcel levels, as they can extend further and further into the troposphere, they can produce larger and larger hail. And our largest hail then is kind of confined to the storms that reach these really tall heights. So we see that storm depth seems to be kind of a limiting factor on hail size. And so this is important because let's change it to CAPE here. Let's just do, most unstable CAPE, which is what most folks use as kind of a hail size prediction. While greater CAPE may be associated with larger hail, we don't see this relationship at all. We don't see this kind of limiting behavior on hail size. And if anything, our larger stones have less cases that are very extreme CAPE up here. So again, we see some kind of useful signal out of the storm height and potential storm height with that MPL, but we don't see that with our CAPE here. We don't see that limiting relationship. So here's kind of what this looks like graphically. Maybe we have, a piddly 8-kilometer deep storm here. Well, our hail size ceiling is going to be given these results. And if we have a sounding like this one on the right here, are we going to produce DVD-sized hail every time? No. But we have a much higher ceiling for hail size, given this sounding on the. So last but not least, I'll talk about storm relative inflow, because this one can get a little complicated. We know that stronger storm relative inflow can support broader updrafts, and generally, in order to get a supercell hail threat, I saw a couple slides earlier on supercell versus non-supercell hail threat. You generally want stronger storm relative inflow to support a supercell. However, there seems to be kind of this Goldilocks zone, as there always is, this cutoff where excessively strong storm relative inflow can actually induce unfavorable hail trajectories within our storm and kind of stymie the hail growth process. And so just a way to visualize this would be something like this. If your hailstone starts out with 40 knots of storm relative momentum here in the low levels, you could sure bet the storm is not going to spend very much time within the storm before it exits out. So on the contrary, then, if you have really weak storm relative inflow, then you get these more kind of relaxed hail trajectories that can spend a little bit more time within the storm. So this kind of works itself out as sort of a momentum problem from both our storm relative wind and our buoyancy, where the way I see this is that we have to have sufficiently weak momentum in the vertical and the horizontal. So for an example, right, maybe we have really intense low-level storm relative winds here. What fell out in our data is that when we did have cases like this, we generally had much weaker buoyancy beneath that freezing. So we don't have excessive momentums, both in the horizontal and in the vertical. We cut back on our vertical momentums here with this kind of. And then likewise, if we did have really intense vertical momentum here, these were the cases that generally had weaker shear and weaker horizontal momentums with our storm. So we kind of have this two ends of the hail spectrum where we had our high CAPE or our high shear and low CAPE beneath the hill growth zone. And then we had our low shear and then our high CAPE beneath the hill. So for review, we talked about a few new parameters, especially CAPE and its distribution, the depth, especially up to the maximum parcel level, and how this matters above the freezing level, our storm relative inflow, and then our buoyancy beneath the hill growth zone. And so generally, having more buoyancy above that hill growth zone does not seem to be a bad thing, given anyone's research currently. And this is certainly what I'm working with Mateusz Cezarek, and he's finding that one of the better discriminators of potential hail size is this CAPE, especially above that hill growth zone layer. So this is generally a good thing. Generally, wider updrafts can also produce more hail mass and potentially larger stones. This has been simulated, especially by Hungen's group. And then updraft depth seems to be kind of a limiting factor on hail size, whereas taller storms with a deeper depth here, especially above the freezing level, have the potential to produce larger hail. And this relationship with hail size is a little bit more muddy if you look at CAPE. It seems that the actual maximum acceleration of the updraft might not be as important as simply just how deep that updraft gets. But we're going to need a lot more research to actually conclude that. And then, of course, the storm relative inflow problem. Generally, we're just looking for kind of a moderate amount of storm relative inflow. Seen from Matt, if you've seen from several others, generally our more moderate shear seems to be more conducive. 2 weak shear, and we don't have large enough, robust enough supercells. Too strong of shear, and we start to play with our hail trajectories. So now that we've gone through that, we'll look at a few case studies, and I encourage anyone to shout out if they think this looks like a tornado day or a hail day or both. What do you think about this sounding? I want to step up.
I'll say tornado.
Yeah, so this is actually both hail and tornado. Lots of strong tornadoes up and down the dry line, West Texas and Western Kansas, and then also some very large hail. I think this was a pretty favorable environment here. You had a strong cap here, which was kind of reducing your low-level accelerations here. And then you also had a fairly small hodograph with a relatively weak storm relative inflow, but nice curves here. There's lots of mergers on days like today. That loop I showed earlier of all those supercells merging together, this was that day. So we had a lot of chaos going. What about this one though? Maybe a better question would be, would you expect significant severe hail with this kind of sounding?
I would say no with that freezing level so high.
Yeah, there's a couple things working against this. And this is just an absurd hodograph. And really interestingly, we don't see this hodograph appear in our hail events. Like if it does, it's exceedingly rare. I think there's a few things going against it. I think that Matt Cumgen study back in I think 2016 simulated that much stronger low-level shear tended to create these really unfavorable hail trajectories in our storm. And then of course the storm relative inflow. So we have both the effects of really strong little shear storm relative inflow. These supercells were highly tornadic too, which I think further cut down on hail potential. And of course we had the really high freezing level with lots of CAPE here below that, and a very low LFC. So we actually get these kind of soundings in the Southeast US very frequently. And we generally see these go without producing large swaths of significant hail or even hail in general.
2-minute warning there, Cameron?
What's that?
2-minute warning?
Okay, awesome. Yeah, I'm about done. So I'll kind of just tease what I'm currently looking at right now on storm interactions. We saw that there's kind of this limit to predictability using the environment. So we wanted to take a look at what kind of storm interactions are conducive to large hail. And this is a completely different topic and talk, so I'll just kind of tease this. But generally, we unsurprisingly found cell mergers in a large quantity of our cases, or updrafts that come together. Generally, the better they were at producing really large hail. But what was perhaps most interesting is that we found that in more than 40% of our cases of 3-inch and greater hail, our storms were associated with cold fronts and boundaries. And they're kind of elevated on the cool side of that. And if they're in these convective systems, or typically at the tail end, kind of at the base of all this regurgitated outflow air from the system itself. And then if they're in pairs of supercells, the most prolific hail producer was typically on the tail end of that pair. So generally what we found is that hailstorms are very often elevated, perhaps more typically elevated than we even think they are. And even in environments that ostensibly seem to favor surface-based convection, storms producing really large hail tend to find a way to be elevated, at least locally, behind kind of like a boundary or supercell. So that's all I got. And if we got any time for questions, I'd love to take those.
Thanks, Cameron. That was fantastic stuff. Someone who has to to forecast hail, this is all very important.
Yeah, appreciate it.
Use. We have time for one quick question, and that came in through the event Mobi. So it's, have you looked at the environments that favor large volumes of small hail? These types of storms often cause agricultural damage in Canada.
Yes. So, and I luckily have a couple slides on that. Let me go back up. Yeah, so the large accumulations of small hail, we can break that down into two problems. So we're dealing with small hail. So what is a small hail environment? Well, it's typically one with a relatively small supercell and an unfavorable profile. So maybe we have this one where we actually have a very favorable distribution of CAPE, generally weak below that freezing level, but enough CAPE above this. This is a really shallow storm. This is just one example of a storm producing large accumulations of small hail. So we had a really shallow storm, so we kind of, have a low ceiling on potential hail size. And then, there's that concept of accumulating hail, and really all that I've been able to find so far is just slow storm motion. So if your storm is moving relatively slowly, hail will fall in one place for a longer period of time, and then you can get larger accumulations. So generally, we are looking for like environments like this with rather small shear, maybe mediocre CAPE, and then slow storm motions for these large accumulations.
Great, thanks, Cameron.
Yep.
Well, we really appreciate you accepting our invitation to be a planet or a keynote speaker for this session. So thank you very much.
Thank you so much. It means a lot. I'm glad you guys got some from it.
Yep, for sure. Okay, take care.
Thank you, have a good one.
Thanks again, Cameron. It's excellent.
Yeah.
Okay, our next speaker is John Hanesiak, and the title of his talk is ERA5 Alberta Hail Environments during the 2022-23 Northern Hail Project's field season. So see if you can take it away there, John.
Okay. I've been trying to fiddle with my screen here, Dave, and I don't know, I'm not sure this is going to work very well. I'm hoping it will. What do you see?
Well, I can see your slide, but like I said, it's pretty small, but you can still read it, so.
Okay, my apologies for that. I don't know what's happening here. So anyway, okay, thanks, Dave. Yeah, this is a good sort of follow-on talk to what Cameron's been talking about, I think. So we've been doing a little bit of work in Alberta as part of the Northern Hail Project, which I'll talk about. So some of my co-conspirators here are Dylan, who is a Northern Tornadoes Project research meteorologist. Dave Walker is a colleague here at University of Manitoba who has expertise in spatial stats. Mateusz, who Cameron talked about or mentioned. We've been working with Mateusz to try and expand some of the work that Cameron and Matt Cumgen in the States have been working on, so to expand that in Canada. Julian Brimala, of course, is the Northern Hail Project Executive Director, and Clinton is a master's student of mine under the Northern Hail Project. So I think, as we all know, there's been some time since there's been a dedicated hail research program in Canada, so there's been a pretty significant gap in trying to advance knowledge in hailstorms in Canada. So it's, which is critical for improving forecasts and impact assessments and risks and so on. So, and of course, as Laura has showed in this morning's plenary talk, so lots of insured losses for severe storms, including hail in Alberta and elsewhere. Manitoba's, other parts of the country have seen some significant hailstorms. So in terms of, there was, of course, lots of work done in the late 60s, 70s, and mid-80s with the Alberta Hail Project. And we still need to go through a lot of the data sets from those various field programs. That's going to be a huge task that we have to do to, make sure we're utilizing some of the work that was done back in those glorious hail days. So they've focused on, convective indices for different storm modes, radar eclitop correlations, probability of hail on the ground, of course, planetary boundary layer evolution, which Jeff Strong was heavily involved in. I bolded Julian Brimlow's work in 2002. He sort of tried to summarize a lot of the good stuff that came from AHP. So for those interested, you can look at Julian's paper back in 2002 where he's using Hailcast model. And internationally, there's been a lot of work. Of course, Cameron has been sort of a big part of that. Matt Cumgen, lots of European people as well. There's been a huge resurgence of hail research, which is really good timing. Lots of things going on. So people looking at close proximity soundings, reanalysis and modeling studies. So here's just a few. Like I said, Matt and Cameron's work, really good stuff. And once again, the AHP, we need to sort of look back to see what was done there too. So basically the idea here is trying to extend what people are doing in international scene to, extend it to what we're wanting to do here in Canada as well. So a lot of the studies, like I said, Cameron sort of pointed out a lot of the good things, various different types of cape, storm relative winds seem to be important, the depth of the sort of the altitude that the parcels travel, right combination of low and mid-level shear, tropospheric humidity, and so on. So lots of things, lots of exciting things to look at. So the Storm Prediction Center in the States actually uses for their hail parameters, they use sort of CAPE between -10 to -30, so that's sort of the hail growth zone. They use 0 to 6 kilometer shear and then the freezing height. And we'll see how that sort of pans out some of the stuff that we've been looking at here. So for those who aren't familiar with the Northern Hail Project, it's a NSERC Alliance MyTax grant. It's a 5-year project. And sort of the goal of NHP is basically to advance the meteorology, climatology, and impacts of hailstorms in Canada. And there's lots of different tasks that are involved in the project. And what I'm going to be focusing on here is task 5, looking at hailstorm environments and the numerical modeling component of that. But I'm going to focus mainly on basically trying to characterize hailstorm environments. So this is just the beginning of our work. There's lots of things we still need to do. We're working with Jason Milbrandt, Environment Climate Change Canada, to look at the 1 kilometer model simulations that he has available. So we'll be looking at that later down the road, but I won't be presenting that here today. So just give you background. So what we've been doing is just gathered ERA5 profiles in the vicinity of the NHP hail events. So there's about 52 events in 2022 and 23. And you can see the dots here kind of shows where they all were located. We identified supercell and non-supercell storms. So the red ones are supercells, blue are non-supercell. And basically what we wanted to do is compare supercell hail to non-supercell hailstorms. And we also looked at supercell hail versus strong tornadoes, which Cameron sort of looked at in some of his PhD work. I won't present any of that stuff here just because of time. And we're looking at we're still looking at hail sizes. So how do we, how do the environments change according to hail size categories? So we'll be doing some of that. And then, so I'll be focusing mainly on supercell versus non-supercell events. So there's 20 supercell versus 32 non-supercell. And then I just wanted to sort of look at a giant hail case that happened in Markerville in 2022. Is basically the largest hailstone ever recorded in Canada. So I want to sort of compare that sort of environment to kind of the more typical ones that we sort of saw during NHP over the last couple of years. So here's composite Skew-Ts of supercell on the left, non-supercell on the right. It's very similar to what Cameron was just sort of showing in some of his soundings. So one of the big things is the equilibrium level higher for supercell events. So it's once again the storm tops are like close to 11 kilometers versus 9.5. And once again, it's very similar to what Cameron was talking about in terms of hail sizes and hail production. The non-supercells events seem to have skinnier cape and less cape overall. So I think I put this thing here. So ML cape for supercells on average about 1,300 joules per kilogram, whereas the ML cape is actually sub 1,000. So it's not a big shocker. The cape in the hail growth zone is larger for supercells. So once again, Cameron sort of pointed out that. pointed that out. And the significant thing here, though, is the freezing levels are typically lower to the ground in non-supercell events. So typically 500 meters lower to the ground. And once again, as Cameron pointed out, you need typically with lower CAPE environments for the non-supercell events, you need lower freezing levels to basically accommodate, hail growth. Here is a composite hodograph. This is a non-rotated hodograph, so this is basically average of, so once again, the red line is the supercell hodograph, and the blue is the non-supercell. So supercells generally had larger hail, which is obviously somewhat expected, more shear, more CAPE. The one thing that sort of stood out with these, of course, is larger 0 to 1 kilometer shear and the hook size for the supercells, whereas it tends to be a little bit more straight line, of course, for the non-supercells, which once again isn't much of a shocker. But the big thing we found, and this actually goes for supercell hail and even tornadoes, is we see larger 1 to 3 kilometer, 1 to 6 kilometer shear for supercells, and that seems to be the big difference. And some of the work back done in the early 70s, a lot of the photographs we see here are fairly similar to that, which is good to see. But of course, strong low-level, as Cameron showed, strong low-level storm relative winds are sort of detrimental for hail, but it's a little bit more complex, of course. So we know the trajectories of hail are fairly sensitive to storm relative winds, and Matt Cumgen's modeling work sort of suggests the same thing. So in our case, we sort of see similar large mid-level shear overall for supercell cases. So maybe we get sort of the right balance between hail-grown zones CAPE and mid-level shear for our events. Some people have done rotated photographs. So on the left-hand side here is Mateusz Tscharik's method, and then Cameron Nixon method on the right-hand side. So the idea behind the rotated photographs is to account for some sort of storm motion and to sort of try and standardize the photographs in some sense. But basically they basically show the same thing. Is the big difference is the shear between the 1 and 3 kilometer to 1 to 6 kilometer levels that distinguishes these different storms. And of course the hook shape is a little bit different too. Yeah, so once again, it's very similar to what Cameron was doing for some of his PhD work, which is good to see. I'm not going to go into this slide in any great detail. So what we wanted to do here, the idea is to come up with convective parameters that we can use to better distinguish between supercell and non-supercell hail events. So, and these are a bunch of the different parameters, and I'll sort of concentrate these in the next slide. So we sort of concentrate, we looked at, so Mateusz has some code to basically calculate a whole bunch of different convective parameters based on the ERA5 profiles. And so we use those to try and see, which parameters tend to be the best at distinguishing between supercell and non-supercell events. So we look at different categories, so parcel versus thermodynamic parameters versus kinematic parameters, and then composite parameters for sort of a combination of kind of thermodynamic and kinematic profiles or parameters. So we used, once again, I won't go into a lot of detail with this. We can talk offline. This is fairly similar to the paper we just did on our strong tornado paper. So basically used random forest techniques, PCA and MANOVA tests to try and tease out which parameters tended to be the best. And this sort of slide just shows sort of the top 3 events or best discriminators. So MUE CAPE, so it's basically most unstable entrained CAPE. So that's sort of accounting for entrainment as the parcels rise through the atmosphere. So the tropospheric humidity is important for that. MUE CAPE underscore SM. So SM is just for the non-supercell storms don't have a storm motion that supercells do. So they tend not to right move quite as much as supercells. So that's where the SM comes in. It tries to account for non-supercell type storm motions. And then of course, freezing height, which isn't a big shocker either. On the kinematic side, of course, bulk shear, the effective bulk shear is the important part. So the effective layer is important, whether you're looking at most unstable parcels and even mixed layer parcels. And the other parameter we found was somewhat helpful is the bulk shear between 1 kilometer to the minus 10 degrees Celsius level. So that's actually sub-hill growth zone. So that's sort of that's interesting because Cameron sort of did talked about the importance of shear, storm relative winds below the hill growth zone, and in combination with the Cape in that area too. In terms of composite parameters, sorry for the acronyms, but the EEMU is just the entrained effective, most unstable portion. So you have to account for the entrainment side of things, seem to be important. The Wmax shear is a parameter that Mateusz came up with. It's basically a multiplier of bulk shear, effective bulk shear, and the Cape. So basically the strength of the updraft. So, and then there's a couple other parameters here, which I won't go into just in terms of time. Sherby, some people might be familiar with it. Yeah, so the Sherby is just a severe hazards in environments with reduced buoyancy. So it's sort of designed for low Cape, high shear environments.
2-minute warning there, John.
Pardon me?
2-minute warning.
Okay, thanks, Dave. I'm getting there. Okay, so what's with all the parameters? Parameters galore. There's a whole bunch of parameters. So lots of different studies have sort of looked at, and there's different parameters that seem to be important for different regions around the world. So it just could be due to different environments and things like that. So just to give you a feel for so difference, some of the numbers looking at supercell versus non-supercell. So MU E Cape, so roughly supercell is 1,000 joules per kilogram, whereas it's closer to 500 joules per kilogram. And then of course the effective bulk shear differences. So once again, the parameter that seems to work best is this entrainment effective, most unstable Wmax shear. That seems to be the best one that sort of discriminates between the two types. Okay, so just quickly looking at the sample sounding for the largest hailstone that we had in Alberta, basically in Canada. If you sort of look at the Skew-T on the left-hand side here, the troposphere is very moist. The principal waters are extremely high for Alberta. LCLs were lower to the ground. Cape was basically double the typical values, and the equilibrium level is actually very high in this case as well. Very weak low level shear though, and that's very important. So low level shear is in the low levels is actually quite small compared to the upper levels. Here's the actual picture of the hailstone. So 2.3 centimeters, almost 300 grams. So I just want to make this point here. So a lot of these things I've pointed out already, but one of the things that Cameron Nixon's work showed, if you take the ratio of bulk shear from 0 to 1 kilometer and divide it by the bulk shear 1 to 6 kilometers, and if you do the calculation, for this particular giant hail event, we get 0.13. And what we found is if you have numbers lower than 0.4, 0.5, it's typical for large hailstorms, but not tornadic storms, which is kind of interesting.
So
Okay.
that's 15 minutes, John.
Pardon me?
That's 15 minutes.
Okay, sorry. Okay, I'll end it there. Sorry.
Great, thanks. Yeah, so I think we'll just move on to the next presentation as John puts his conclusions up there. And that is Scott Kehler, and it's the Canadian Hail, or the title is Canadian Hail Data Developments at Weatherlogics. And let's see, is Scott ready to go here? There he is.
Thanks, Dave. Can you see the presentation?
Yeah, it looks good. Go ahead.
So good morning or good afternoon, depending on where you are. I'm Scott Kehler with Weatherlogics, and today I want to talk about some of the hail data developments at our company. We've already been hearing a lot about hail forecasting, which is sort of a crucial piece to improving our understanding of storms in Canada. And at Weatherlogics, we've been tracking and collecting data on hailstorms for many years, which is a useful tool to help provide the ground truth for underpinning some research. So a little overview here of what I'll discuss today. For those of you who aren't familiar with Weatherlogics, it's a private weather forecasting company based in Winnipeg. We primarily offer services to industries like agriculture, insurance, transportation, and government. And we recently began offering an app which plays into the hail data, as I'll describe a little later. But more specifically on hail, at Weatherlogics, we've been collecting hail data nationally across Canada since 2017. We do have data prior to that for certain regions, but our national database began in 2017. We saw the need for a high quality database of hail in Canada for both real-time and historical purposes. So we're inputting new reports into our database on a daily basis as hailstorms occur. And we kind of modeled our database after the European severe weather database. So we store everything from the report time to the lat long, nearest city, province, and the diameter of the hailstone. We also maintain very strict quality control levels in terms of the accuracy of every report, so we know its accuracy in terms of location, diameter, and time. So in the database since 2015, there's been about 10,000 hail reports, more than that now, as we've been collecting quite a few in the month of May. Every report has the location within 2 kilometers or less, the hail diameter within 5 millimeters or less, the time within 15 minutes or less, and a bunch of other things like the city, province, notes, etc. So if a hail report has these kind of accuracy criteria with it, we consider that to be our lower accuracy report. Our higher accuracy reports are actually valid to within 250 meters in location, 2 millimeters in diameter, and 5 minutes in time. We've also begun supplementing the hail reports, which are actual measurements of hailstones, with crop insurance claims from Manitoba and Saskatchewan in partnership with Co-op Hail Insurance. And this is very valuable because a lot of the time the hail reports are biased toward urban areas, whereas the crop hail insurance data gives us a lot of data in rural areas where hail is often not reported. So just a little quiz here for the folks in attendance. There's nowhere to vote on this, but you can just do it in your mind. Which province has averaged the most hail reports since 2017? So we're looking at Alberta, Saskatchewan, Manitoba, or Ontario. So I'll give you 5 seconds to think about it, and then I'll show the answer. So the answer, it's Alberta, and it's really not that close. In some given years, other provinces do get close to Alberta's total hail number of hail reports, but just over the long term, Alberta is far and away the most hail-prone province, has the most hail reports almost every year, with few exceptions. But in the last 5 years, you're seeing here Alberta led the way. In terms of who's second, it varies. So actually, last year Ontario was second, which is unusual. Ontario is not often thought of as a hail-prone area, but in recent years, there have been a number of significant hail events. Normally, Saskatchewan or Manitoba is second. Probably is Saskatchewan more often than Manitoba, but they tend to trade places. What about severe reports by year? So the previous graph was all hail reports. This one is just severe hail. So again, Alberta leads the way, but depending on the year, other provinces can be competitive for taking that top place. Last year, Ontario and Manitoba were basically tied for second place for severe hail. Alberta still edged them both out overall, but it wasn't too far ahead for severe hail. And then you see some years Saskatchewan actually is way up there. But last year was kind of weird because Manitoba and Ontario were both very active for hail. Alberta was kind of active as it normally is, but Saskatchewan was way down for hail reports, despite the fact that it's right in between Alberta and Manitoba. And 2024 is off to a very busy start. For our database, it's already a record up to this date. And given that May is not normally a super hail-prone month in Canada, the fact that we're already so far in the lead for number of hail reports suggests 2024 might be overall the most active hail year we've recorded. So on the left, you can see all hail, or sorry, on the left, you see just severe hail reports greater than 2 centimeters in diameter. So this year is already far and away leading that count up to this date, which is May 31st. And for total hail reports, which includes hail of any size, 2024 has already doubled the previous record year, which was 2017. So we've had over 380 hail reports of any size up to the end of May. So very busy start to the year. And that comes from really all across the country. Ontario has been very active. Manitoba has already seen a significant hailstorm in Winnipeg that caused damage in mid-May. So interesting to see how the hail season is off to an active start. Plotting all the reports across Canada since 2015, you see that the two areas that really jump out are the agricultural part of the prairies, especially the kind of Calgary to Edmonton corridor, often called Hail Alley. And then Saskatchewan and Manitoba, very hail prone as well. Lots of hail reports over the past 10 years. Southern Ontario and Quebec being the second area that jumps out. But really, no matter where you look across the country, what you'll notice is a real bias toward both urban centers and agricultural areas. That's because basically the population density is higher in these areas. And so it's easier to identify where hail has happened because people are there to observe it. Whereas in the boreal forests, we see a lack of reports. Now, given that it's farther north in a lot of areas, it's not surprising that we would see less hail because the climate, the farther north you go, tends to be less prone to severe weather. But we do know that places, especially like Northern Ontario, do get a lot of hail that goes unreported. And so I know the Northern Tornadoes Project has also shown in some of their research that there should be more tornadoes reported in areas like Northern Ontario. And I know they have been identifying them now with satellite imagery, but historically those areas, our data suggests there probably should be more reports there, but because there's nobody to report it, it hasn't been showing up in these databases. So I've already kind of talked about these reporting biases. If we do see a case where a severe storm goes through an unpopulated area, we'll try to track down what happened there, but it's often very difficult. Let's say Northern Ontario, you might only have a fishing lodge or something in the path of the storm. And so if you're not able to get in touch with anybody there, you might not have any way of determining if hail fell. We, of course, have things like radar algorithms that can identify storms that are producing hail, but they're not always accurate. I mean, they're fairly good, but we want to actually have ground truth data. And so that's why we're keeping track of all of these reports. Historical data prior to when we start our database is a little bit inconsistent, and also it suffers from, it doesn't suffer, but we have to bear in mind that there was no social media, in earlier periods like the 80s and 90s. And so when we do see active periods of weather back then, it's hard to compare them to today because we just simply don't have the means of, or people back then didn't have the means of collecting data the way we do now with the internet. So there's a lot of biases to keep in mind, but nevertheless, the data is all valuable. And using crop insurance claims, what we're able to do is identify where hail has happened in areas where there might be really low population density, and so we might not otherwise see any hail reports. Now, a crop hail claim doesn't give us the diameter of the hailstone, but it tells us that hail happened, and it also gives us the percentage of loss on the crop, so what percentage of the crop was destroyed or damaged by hail, and that can be a proxy for the hail intensity. And the good thing is that the crop insurers measure damage down to what they call the quarter section, which is a quarter of a square mile. So the data resolution is actually very fine. It can be as low as 400 meters in resolution for crop hail claims. And so that's also very valuable. And so we're able to make maps like this, where we break the prairies down into a township's grid, which are the thin gray lines in the background. Every township is 6 miles by 6 miles. And so we, on this map, are counting the number of hail events per township per year. So this was what we saw last year. And so you can see there's a lot of data there in very rural areas that might otherwise have been missed. Our app is a new means of data collection that we've been slowly rolling out. We did some beta testing of it last summer. And so the map that you're seeing here shows hail reports we received from the really damaging Winnipeg hailstorm last August through our beta testing. So in the talk at the start of the day, Laura from Cat IQ mentioned that this was a $230 million hailstorm. And with our app, we were able to see in real time where hail was falling and what size it was as our users were reporting it through the app. Now, this summer, in partnership with the Northern Hail Project, we've rolled this out to a live version. It's available for free to download for anybody. And we're allowing people to report hail that they're seeing, both the diameter, time, and location, as well as any damage that they're observing. And so that's now all going to be available through our app, and you can view it in real time on this map within the app. So you can check that out. We've also been working on processing radar data. So this is a radar map using the mesh algorithm with our hail reports overlaid. It's probably a little hard to see all the reports, but every little red dot is a hail report showing the hail diameter. So we can verify these radar algorithms using our hail reports. And because we're collecting so many of them, you get a really detailed view of how the algorithm is assessing these storms, whether or not it's accurate. We're also creating other maps with kinetic energy because sometimes the hail size is not directly correlated with damage. Sometimes a lot of small hail produces damage or very little hail, but if it's large, doesn't produce much. So kinetic energy is a way of taking the size of the hailstone, its terminal velocity, and the time it dwelled at a location to determine the total intensity of impact, and so therefore perhaps a better assessment of the damage. So here's two maps showing that. So on the left, we have a map showing what the maximum estimated hail size was. And then on the right, you see the kinetic energy. So a lot of the swaths of hail, just strictly based on its size on the left, might not have actually produced a lot of impact energy and therefore not a lot of damage when we actually consider the time the hail dwelled at a location along with its total impact. But you do see a little swath to the north side of Winnipeg with high kinetic energy where there was a lot of damage. At Weatherlogics, we also produce hail forecasts on a daily basis. We sometimes release these to the public through our social media. This is just an example of one we did last summer on the day of the Winnipeg hailstorm. So we were anticipating isolated severe storms. That day, the Winnipeg storm was quite isolated. It was a very small supercell, only affected the north side of the city. But these types of maps help give people a heads up on what to expect for severe weather on a given day. And here's the hail swath.
2 minutes, Scott?
Okay, thank you.
Yeah.
Future advances, working with dual pole radar to try to produce more accurate hail mapping, and also use radar data to actually estimate hail damage from impact. So now how does the size and the volume of hail determine what the damage is? Finally, expanding hail climatology with our partners like Co-op Hail Insurance to integrate crop insurance claims.
Great, thanks. And I'll see if we have any questions here. Yeah, we do have some. Let's see. I'll start at the top here. Are you aware of the joint effort by ECCC and NHP to integrate hail reports collected within ECCC?
We're a partner with NHP as well, so they're using our hail reports, I assume, as well as ECCC. So we're kind of all pooling those resources.
Okay. Next question. What kind of quality assessment is done on those public hail reports?
The quality assessment is the location of the hailstone. So we make sure that we know the location at minimum within 2 kilometers for our lower quality level, but ideally within 250 meters for the higher level. We also check the diameter. We either need a reference object to verify what the diameter of the stone is or an actual measurement of the stone to ensure it falls within quality bounds. And then the time as well can be verified many ways, including using weather radar.
Okay, thank you very much. I think we'll move on to the next presenter. Thanks, Scott.
Thanks, everyone.
And the next presenter is Milena Alpizar, and the title of the talk is Mesoscale Convective Systems and Extreme Precipitation in Northeastern North America, Identification and Evaluation with the Canadian Regional Climate Model, or CRCM6. And I see the slides up. That's good.
Okay.
Great,
Thank you
thanks.
very much. Good afternoon, everyone. Today I'm going to present the Mesoscale convective systems and extreme precipitation in the Northeastern North America, and identification and evaluation with the Canadian regional model. I'm a student at UQAM, supervised by Philippe Cachon and Alejandro Di Luca, professors at UQAM also. First, I want to start by identifying what mesoscale convective systems are. They were defined by Hughes at 2004 as cumulonimbus systems that produce an area of precipitation that extends at least 100 kilometers in one direction. They are responsible for a variety of meteorological hazards at regional and local scales, producing hails, high winds, extreme precipitation, floods, and landslides. They also can contribute to more than half of total precipitation in some mid-latitudes and tropical latitudes. One example of this MCS is the derecho that affected the southern part of Quebec and Ontario at May 21st, 2022, and this derecho is considered the sixth costliest weather event in the Canadian history. Although these MCS have been widely studied around mid-latitudes and tropical latitudes, we have seen that there is little known about them in the eastern part of Canada. That's why we have as objective analyze the mesoscale convective systems in the northeastern region of North America during the period from 2015 to 2021. To do that, we have selected a set of data from numerical simulation and from observations. In the case from numerical simulation, we have the simulations from the Canadian regional climate models, the sixth version that is developed at UQAM. And these numerical simulations has two configurations. The first one has a horizontal grid spacing of 12 kilometers, and the second one has a horizontal grid spacing of 2.5 kilometers with a conversion permitting mode, and has a domain center over the southern part of Quebec, that is the blue square represented in the figure at the left side of the slide. Both simulations are run with boundary conditions from ERA5, and we will analyze only the period between 2015 and 2021. We have selected the reanalysis from ERA5, the data from ERA5, and data from the satellite observations from IMERC and Mercury. It's important to note that all data is conservatively interpolated to the grid of the model at 12 kilometers. In order to analyze the MCS, we need to use an identification algorithm that allows obtain a climatology of this MCS over the domain of the study. To do that, we have selected a tracking algorithm that has been implemented in Python by Prime in 2021 and improved by Arguez in 2023. This algorithm uses as input data the precipitation and the brightness temperature, as we can see in the figure, in the first figure at the left, top left side. As a second step, the algorithm apply a binary mask to identify the regions of interest. In this case, for the precipitation, we are interested in the areas with precipitation above 5 millimeters per hour, and for the brightness temperature with values less than 241 Kelvin. Those areas are labeled with identifying number to separate the different objects in each one of the variables. And then as a fourth step, we apply an overlap mask between the precipitation and the temperature variables to select the common areas between both. Once we have identified the overlap areas, we want to check if these areas are meet the conditions to be considered as MCS. In this case, we have set some conditions for the minimum area, minimum lifetime, minimum precipitation, and brightness temperature. And once we know the objects that meet this condition, we will label with different identifying number through each time step for each MCS. This algorithm also allows to obtain different characteristics for each MCS, such as the center of mass, the translation speed, the mean precipitation accumulated over the entire area, the total precipitation, and the area of the system. Each of these characteristics are obtained for each MCS at each time step of their lifetime. One of the first results that we have obtained in the domain of study is the monthly distribution of MCS over this domain. The colors represent the combination of different data, as I mentioned before, and we see if for the names that has two different name data, that represent for the first name correspond to the precipitation and the second correspond to the brightness temperature. We can see that the month that where the MCS are most common or more frequent are between June and September, and we can see a high number of MCS that are identified by the model at 2.5 kilometers that can be identified by other data such as the model at 12 kilometers and the results obtained with the data from ERA5. That suggests that the model at 2.5 is capable of identifying convective activity that might be missed by the other data used. If we analyze also the diurnal cycle of the MCS initiation time, taking the first hour of formation of the MCS identified by each test we have used in the algorithm, we can see a diurnal cycle that has higher frequency of formation around 17 and 21 hours of the day, mainly for the model 2.5 kilometers that have a higher frequency. And if we see also for the results obtained from the precipitation from ERA5, a high frequency at 7 and high at 19 hours, and that can be related that the ERA5 assimilation system use short-term forecasts that are generated at 6 and 18 UTC to assimilate the observations, and we can see the same pattern here for the diurnal cycle. We want also to include the analysis for different characteristics obtained from the algorithm. For example, the object size, the areal maximum precipitation, areal mean precipitation, object speed, the lifetime, and the length of the trajectory for each of the MCS identified. The analysis of the probability density fusion shows that the model at 2.5 is identified with higher frequency the smaller objects with a typical size around 10,000 square kilometers in comparison with the other data that the systems tend to be larger. In this case, also we can see that these smaller objects has a maximum or larger values of maximum precipitation and larger values of mean precipitation that is greater than the other data. And the result for the ERA5 are the lesser values for the maximum and mean precipitation from these systems. If we analyze the object speed, there is a slightly slower speed from the systems identified with the model at 2.5 in comparison with the model at 12 and the data obtained from the satellite. And those are also shorter in the lifetime and has a shorter track length. The results obtained with the satellite data are similar with the model at 2.5, mainly for the lifetime and the track length of the MCS. We have also applied a regression analysis using the lowest method and Spearman rank correlation coefficients that has been used before by Prime in 2020 to analyze the interrelation between these properties. I show on one example here between the total precipitation, maximum precipitation, and the speed versus the object size. We have found that for the relation between total precipitation and object size, there is a linear relationship, and there are the higher values of Spearman are found in these variables. Although the relation between the other characteristic is not direct linearly, and the Spearman rank correlation coefficients are smaller than the others. That suggests that the object size of the MCS are a key factor determining the total precipitation accumulated by the MCS in the area. In general, we have seen that as a conclusion that during the summer months from June to September, there is a higher frequency of MCS events that they typically begin in the late afternoon. That we have found that lower resolution products, including the model at 12 km and ERA5, do not fully reproduce the MCS. The product IMERGIR, the satellite product, performs better in capturing the MCS. However, its reliability as a reference to evaluate the model at 2.5 remains uncertain. Compared to all other products, the model at 2.5 shows a pronounced diurnal cycle of the initiation of the MCS, and we found also, as I said, a higher correlation between the size and the intensity of precipitation in comparison with other characteristics. A final conclusion, compared to all other products, the Canadian Regional Climate Model at 2.5 kilometers identifies a significantly higher number of MCS that have smaller areas and higher total and maximum precipitation rates. Thank you very much.
Thanks, Milena. So just looking for questions here. I have a question. The 2022 derecho, which was an MCS, as you mentioned earlier, that actually was started overnight and didn't really start producing a lot of damage until maybe 10, 11 o'clock in the morning and onward from there. And yet, you know, the study that you've got shows us this afternoon bias. So what are your thoughts on that? Do you think it's capturing the diurnal evolution of the MCS properly, or is there a problem there?
We haven't studied specifically the derecho of 2022, but we know that the derecho is an extreme type of the MCS. It is known that maybe the precipitation is not so high for this derecho, but we know that has caused high winds, damaging high winds, and that is also another element that we want to study in the further works, in further months. But
Okay.
we have to include this in.
Sure. Okay, thank you.
Thank you very much.
And the last presenter of the session is Melissa Cholette. And the title is Simulations of Storms and Precipitation Types, the Impacts of Recent Innovations to the Predicted Particle Properties, or P3, Microphysics Scheme. And I see the talk coming up, so take it away, Melissa.
Thank you. Can you hear me well? Oh,
Yes.
I put stop sharing by error. I'm gonna start over. All right. Yes. All right. Hello, everyone. Thank you for the opportunity to present here. Oh, I can't rid of this. Okay, like that. All right. Okay, I'm sorry. So I'm a research scientist at ECCC, and I'm also working closely with Jason Milbrand and Hugh Morrison on the P3 scheme. I'm going to talk a little bit more about the P3, but the title of my presentation is the simulation of high impact weather precipitation type using P3. And most importantly, also the recent innovations and their impact on the simulated precipitation types. So as we all know, the various precipitation types that occur in Canada, hail, freezing rain, wet snow, and so on, are often associated with costly and negative consequences. And what we also know as forecasters is that the spatial distribution and the timing of the transition of precipitation types are quite challenging to forecast, as we can see here in the animation. So many numerical weather prediction centers, but also like climate models, use implicit method to determine the surface precipitation types. And what I mean by that is also the phase of precipitation. So either is it rain or snow. So for example, like the Bourgoin algorithm. The Canadian high resolution deterministic prediction system is not an exception. It's using the Bourgoin algorithm to forecast the phase of precipitation. But it is also used, it's also using the P3 scheme. P3 is for predicted particle properties, both microphysics scheme, to predict the hydrometeors evolutions of cloud, rain, and ice. Ice can be also like unrimed or partially or fully rimed ice crystals. So on the left here, we have an example of the Bourgoin algorithm, which is based on the vertical profile of temperature. And on the right, we have an example of a determination of precipitation types based on particle properties. And this is really subjective. It all can be changed. But what it is showing here is that we can predict all the precipitation types using properties such as the liquid fraction, the ram fraction, the ram density, the mean mass weighted diameter, and so on. So what it is P3, the first version was in 2015 from Morrison and Milbrand. And since then, many optional innovations and also their combinations between them have been made to it. So for example, in 2016, the multiple ice categories was introduced. And in 2020, the cloud fraction component. In 2021, the triple moment configuration of ice. And in 2023, the combination of all this with mixed phase particles. So what all these options do, it's depend on every option. But for example, the multiple categories of ice permit to include the secondary ice production. So it allows many types of ice to exist in the same grid point. For the cloud fraction, it's usually for large scale models and its application for low resolution systems. The triple moment ice will have the variable width of the ice size distribution, and that will allow for the large particle and the size distribution, which is really important for hail, as I'm going to show later. And finally, the mixed phase particles predict the liquid fraction of mixed phase particles. And this is really important because it includes many processes such as partial melting and refreezing for ice pellet and wet snow formation. So I'm going to talk a little bit more about 4 cases just to show the benefits of using these options on the simulation of precipitation types. So the 4 cases are listed over here on the right. There is a squall line over Iowa, the Calgary hailstorm, and 2 cold weather cases. So the freezing rain and ice pellet storm and a snow squall that happened in October 2018 over the Great Lakes. The configuration idea, so all simulations use 2.5 HRDPS forecast system, except for the squall line case where I did go to 1 kilometer to have a better resolution there. And here on the table, we have some of the innovations in P3 that will benefit, that is expected to benefit some of the precipitation type and the properties. So the triple moment ice, a diagnostic of the maximum L size, the liquid fraction of mixed phase particles, and improved diagnostic reflectivity calculation with the liquid fraction, and improve explicit precipitation types diagnosis as well, and the multiple ice categories and SIP for secondary ice production. So the first case is the squall line over Iowa, which is published here on the paper written on the top. So what we found is that triple moment and liquid fraction increase the couple speed by 5 kilometers per hour, as we can see here in the top left panel. And this is because there's a higher total cooling from the microphysics with liquid fraction on. As we can see, we add a new term, which is mixed phase particle evaporation. On the right, it's also an illustration of how the reflectivity is quite improved with the liquid fraction and a triple moment. So the triple moment seems to improve the convective core reflectivity simulation because it allows for larger particles. And the liquid fraction allow to have the bright band because of the mixed phase particles. Here, the second case, it's the hail case over Calgary that happened in 2020. So what we found is that for hail accumulation, the operational P3, the one used in the HRDPS right now to do the forecast, doesn't have any hail accumulation over Calgary. When we include triple moment and liquid fraction, we increase this accumulation and get a reasonable max hail size as well compared to the mesh product. But what we found is that we need 3 or more category of ice to represent better the hail properties of both accumulation and max hail size. Now for the winter cases, the first one is a freezing rain and ice pellet. Here we have an example of one case where the explicit freezing rain of P3 was completely overestimated in the north part of the maritime provinces. And that is also compared with observations. And that no ice pellet was given in that simulation. I mean, the explicit P3 ice pellets. So when we include 2 ice categories in the secondary ice production, we actually reduce a lot of this freezing rain accumulation and produce more ice pellet and snow. Snow is not shown here, but we can clearly see that in the early precipitation type in Newfoundland here, compared to the observation. We can see that the freezing rain is completely decreased in the simulation and snow is upturned instead. And this seems to be a systematic behavior with including, so it looks like SIP, it's clearly increasing the it's improving the statistic for freezing rain forecast. And this is the FBI for 40 cases. We can see that it is clearly decreased. But the last case, it's just showing the benefits of using a liquid fraction, because we can now include some of the wet snow particle and diagnose them. So this is a case over the Great Lakes where rammed ice was quite accumulated over Lake Erie here, and also freezing rain in some of the configuration of the scheme. But it's really nice, it's that we can now see that the wet snow, part of the rammed ice was wet also, and also not rammed. So the total wet snow was kind of everywhere over the storm. And when it accumulates fast, it can cause a lot of damage on the ground rapidly. So in conclusion, the recent innovations to P3 impact the forecast of high impact weather precipitation types. We show that the triple moment ice configuration and the liquid fraction of mixed phase particle increase the speed of a squall line. We will have to study more squall lines, make sure that this is the case for other squall lines. Triple moment and increasing the number of ice category improve the representation of hail properties, such as the accumulation, but also the diameter and the max size. And then the last conclusion is that SIP and liquid fraction decrease the freezing rain overestimation, which improve the forecast of it by giving more ice pellet and snow instead. And also, like all precipitation types can be determined using particle properties, and I think it's one of the points I wanted to do here, which I showed with the 4 cases. For the future work, we'll continue research and development on P3 for NWP purposes in Canada. And that includes many aspects that we want to improve. The full triple moment, so better resolves processes with triple moment of ice. The pronostic aerosol in P3 as well, a single liquid category, and so on. So yes, so a lot of work to do, but bit by bit we're improving the scheme and making it really a powerful tool to combine some options amongst them to forecast better precipitation types. So on that, I thank you, and I'll take questions.
Thanks, Melissa. That was a great presentation. We have one question that's come up on the event Moby. Is there some kind of data set at analogous resolution, like 2.5 kilometers, that can be used to verify how representative the 2.5 kilometer model is to reality?
Yeah, it's a good question. It's actually it's actually hard to validate microphysics at 2.5 kilometers, but we are working on it. For the precipitation types, what we use at the ACCC is METAR, so it's surface observations of precipitation types. Yeah, I don't know, maybe the use of radar or satellite will help validating the microphysics in the clouds. And I think that's work that can be done in ACCC at large between the groups.
Okay, thanks for that. And I have a question. Is the output from this model available to forecasters?
Well, right now, the version that is running operationally does not include all these options, and it's an old version, but eventually it will. I hope so. And so yes, all these precipitation types are already in the forecast. It's just that now they got improved by the options.
Okay, so the hail diameter is actually something that the forecasters can get from this model?
I don't think right now it is available because as you can see here, it's non-applicable. It wasn't really available in the operational P3 since it's an old version and it's not used in triple moment.
Okay.
So, but yeah, in the future version, I'm hopeful that it's going to be included.
Yeah, that would be great.
Cool.
Okay, thank you very much for your presentation. And that concludes the presentations for this session, which is part 1 of severe and extreme convective storms. Part 2 will start at 2:05 p.m. Eastern Daylight Time. So it looks like we've got about 15 minutes between sessions here. So just enough time to grab some lunch, maybe, at least for those on Eastern Daylight Time. So thank you for your participation, and we'll see you then.
All right, thank you.